Hello, hi everybody, and welcome to Ask Math Anything. I'm your host, Po-Shen, except that, as you can see, I'm actually walking away. And what that means is we're actually going to have some amazing co-hosts who are going to take over today. Now, if you have not been to Ask Math Anything before, let me just let you know how the typical thing works. First of all, the way that you can talk and you can share questions is that you send messages by going to live.potionlo.com/show. And you can see that actually at the top of this YouTube description. It has live.potionlo.com/show. And if you just go into there and type a message, your message should appear on the screen. Now, please do submit your questions because then we're going to use those to go and answer some of these questions, do some interesting mathematics today. I can see them already appearing on my co-host screens. So at this point, I'm already going to go and drop off and say, the reason we're doing this is we want to showcase the great work and the interestingness of the people who we're working with. We have some brilliant high school students who have come to join, and the two people who are coming today are both from Washington State. Actually, we have Isha and Alan, and both of them are extremely good at math. They've been working with me for a while as we teach middle school students mathematics, and they also have many interests. In fact, both of them currently are also working with me on engineering, on software engineering. But with that, let me turn it over to Isha and Alan. Go for it, you guys, and then you guys can also have the questions on the screen.
Yeah, hello everyone. My name is Alon. This is my second time here actually, and I'm so proud to be with my amazing co-host Isha. She applies math in her robotics team that was top 12 internationally. She placed top 5 in a statewide competition, and she programs in her free time. And I want to add to that if you're on our website, live.potionlo.com/show, she actually designed that page. So huge shout out to her for that.
All right, and I'm so excited to be here with Alon, and he is super talented. He is a 3 times Amy qualifier. He is a Math Counts national qualifier, which is super impressive. And also he enjoys playing the snare drum, which is really unique. Cool. All right, so at this point, we're going to be taking your questions and we're going to see whether we can answer them live. So feel free to type your questions in chat and we'll get to them. All right. I see a question in chat and I'm gonna paste on my screen real quick. And it's about Zach. And he likes rolling fair-sided dice and he is going to keep rolling until he gets 3 times consecutively, which is like the same number 3 times. And we want to see at which point will he stop? Or like how many expected number of times will he have to roll the dice in order to like get that number. So the first like step in a like expected number question, I feel like is to find the probability that like the event will occur. For example, there are for the first number, there's like 6 like ways that you can pick a number because it doesn't matter which number you pick. So it's going to be like 6/6 times, and then afterwards you're going to have to pick 1/6 times 1/6. So it's not going to be like 1/6 cubed because the first number can be anything. All right. So once we get that, then we need to kind of find like the expected value, which is going to be like a lot more, it's not that much more difficult. But expected number is basically like the probability distribution essentially. So it's kind of like the mean. So that's kind of like why I figured this out first. So in order to find the expected like number, I think we need to find the frequency distribution. Am I right, Alan?
Yeah, I think so. I think you'd be right for that.
Okay, perfect. So basically we need to find like the wait, I feel like I'm confusing myself here.
No, I think you're right. You're almost there. You just gotta like, I think because you found that the probability is 1/36, right?
Yeah, exactly.
So wouldn't the answer just be 36?
Yeah.
Yeah.
Wait, I thought I confused myself, but
Or
yeah.
maybe no, maybe it's like 38 because like you have to have 3 each time. So what you're looking for really is hold on. You're looking for like the 38th group of 3, if that makes sense. And so what you have is it would be like, 1, 2, 3. That's a group of 3. Then that's another group of 3 actually, and another group of 3, and so on. So
But you
you're
stop
going
at the
for,
first pair of 3.
huh?
But you stop at like the first pair of 3. If basically what I'm trying to say is like if you're doing something like this, in this probability here, I take every like first number individually. Like this is going to be like completely separate from this because this first number is set by that
Exactly.
first group.
Exactly. That's true.
Yeah.
Yeah. But it still works. It's a little bit of an advanced math topic called linearity of expectation, but essentially we can treat them as distinct regardless. And so this one would be the first 3, that would be the next 3, and that would be the next 3, and so on. And so you're going for the 36th group of 3. So you got to add in the first 2 because those 2 don't count, if that makes sense.
Yeah, that makes sense.
Yeah, that makes sense. Exactly. Because you got to have 36 groups of 3s. And then at that point, you would be expected to get in 1. So you got to add in the extra 2 from the start. Does that make sense?
I thought it was like 36, but I knew that I wasn't accounting for like that first number. So thanks for stepping in.
Yeah, because if you think about it, right, if it was like 4 instead, or if it was, I don't know, if it was 10 instead, and the probability was still like 1/36, then it wouldn't make sense that it would be the same thing because you got to.
Yeah, exactly.
Yeah, so that makes sense. Good call.
Right.
Good call. All right. I guess now it's my turn, so that's great. I saw a pretty cool problem in the chat earlier, actually. It was this. It has to do with equiangular octagons, which is kind of scary, actually. Like, so essentially, an equiangular octagon is not like an equilateral octagon. It's actually a little bit different from that because it means that all of the angles are equal, and that does not mean that the sides are equal. For instance, what you could have, I'll actually give an example with quadrilaterals. An equiangular quadrilateral is a rectangle, actually, because if you have like this, for instance, a rectangle, then all of the angles are equal, but not all of the sides are equal, obviously. And for larger polygons, it gets even worse. You can have like really weird things. Like at least for rectangle, we know that these 2 are equal and those 2 are equal. But for like hexagon, for instance, you could have like this kind of stuff, like that, which would work because all of the angles are equal. But like what are these sides? It's kind of weird. So basically, the one thing that I really like to do when I see equiangular here is I like to extend the sides because actually the angle condition turns out to be very, very powerful. And so what I do is, let's say we have just a normal octagon. I know this is definitely not 1, 2, 3, 4, 5, 6, 7, 8. We all know that. But essentially it kind of illustrates what I want to do. If I were to extend these sides, what I obtain is a rectangle, in fact. In this case, it looks more like a square, or actually more like a random figure because I'm bad at drawing. But in general, you get a rectangle because you're not really sure about the side lengths. So essentially, in an octagon, right, this is 135. And so this one over here is 45. And since this one's also 45, that would mean that this angle over here is 90. And same goes for all of these angles as well. So we actually have a rectangle here, which is really cool. But now, what more? Let's see. So this, what is this side? What is that side? Well, we have a 45, 45, 90 right triangle right here. And so if this side is S, then what we know, in fact, is that these sides are S over root 2. And the reason for that is because if you remember, if you have a 45, 45, 90 triangle, then these are in the ratio of root 2. And you can see that by making the square. So you can sort of like complete the square here. Get it? Algebra reference. I don't know if you guys got that. But so you can complete the square. So this side is S, and then these are S over root 2. And so that gives you that. Now, what that means here is since these sides need to be like one of these, we can actually find these lengths given like any assignment of all of these sides. Okay, so we figured out that we can now like figure out what all of these lengths are. That's great. But how do we know if the octagon actually works? The way we know that is because this whole figure is actually a rectangle. And so what that means is in a rectangle, these two sides are equal. So these bigger sides are also going to be equal. Okay, so what that means here is, let's draw a new octagon, a real, wait, hold on, that's wrong. A real equiangular octagon. So that would be something like this. Obviously, my drawing is pretty terrible, so forgive that, please. But it would be something like this. And so if we were to extend these, in theory, if you do it well, unlike me, you would get a rectangle, but I'm too lazy to actually draw it well, because it's not really necessary. Wait, is that even 8? 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's 8. Oh, I'm just bad. Sorry. Okay, there we go. This is our really cool rectangle. Not really, but anyways, that's our rectangle. It's not really a rectangle, but it works for our purposes. So essentially, if we were to like give these like A, B, C, D, E, F, and G, then these side lengths would be A over root 2. These side lengths would be C over root 2. These would be E over root 2. And these would be G over root 2. And so these side lengths actually just need to be equal. Okay, what does that mean? What that means really is that A plus C over root 2 plus B equals F plus E plus G over root 2. Just kind of adding up these side lengths and setting them to be equal. Okay, so looking at this, because all of A, B, C, D, E, F, G, they're all obviously integers, as you know, because they're all 1 through 8. What that means now is that these two, B and F, must be equal. Because if they were not equal, then like these wouldn't really match up, would they? Wait a minute. If they're both equal, how does that work? Because as we know, they all have to be different integers from 1 through 8. So B and F can't be equal. Okay? So what that means is that it just can't happen. Because we know that like B and F, these two opposite sides, have to be equal. Same goes for D and A, and for C and G, and for all the opposite sides. So therefore, you can't have an equiangular octagon with 1, 2, 3, 4, 5, 6, 7, 8. It just does not exist. Exactly. See, Dingle Quandle, he got it. It does not exist. We don't even know it does exist. It doesn't exist. And we just proved that. Because if it existed, then B and F would have to be equal. But they can't be equal from the problem. So that's all. All right.
Oh, yeah, that was super interesting. I think it was a really creative approach to extend the sides because it allows you to like set up the equations and equilateral triangles and stuff like that, which you did. So awesome. I saw this question in chat, and it's basically solving a quadratic equation. So I'm gonna walk through it real quick. So when I first see a quadratic equation, I'm gonna write it bigger just in case if you can't see it well. My first instinct is to factor because I love factoring, and factoring is obviously so much better than using the quadratic formula if you can. So if you take 18, that's going to be like 9 or 2, 3 and 6, but none of those really seem to like correspond well with 6. So I think we do need to use the quadratic formula for this one. So the quadratic formula is just negative b plus or minus square root of b squared minus 4ac over 2a. And I'm going to set a is equal to like the coefficient of like the x squared term. An important thing to note is that don't remember a as like the first term, because otherwise if it was like 6x minus x squared plus 18, then you'd get it wrong because it's always the x squared term. So a is going to be -1, b is going to be 6, and c is going to be 18. And wait, I don't think this is possible, assuming that we're talking about real numbers, because if in order to have a real number, we need to know that the square root, or like whatever is in the square root, is greater than or equal to 0. Because if it's less than 0, then it's going to be imaginary, because you're going to have a negative thing inside the square root. So just to like double check that real quick, we're going to have b squared minus 4ac is equal to 6 squared minus 4 times 18 times -1. Oh, wait, no, I'm just dumb. No, it works out fine. 36 plus 72, and that's going to be 108. So it's going to be, if we plug it back into the original formula, it's going to be -6 plus or minus square root 108 divided by -2. And then you can simplify that further, but like, I don't think we need to. I think that this is pretty decent.
Yeah, I just wanted to use that example as a way to like just show something that I like to do whenever I have these things. So yeah, if you have like -x squared plus 6x plus 18, I always like, or really anything where the leading coefficient, the first coefficient here, is not 1, I always like to force it to be 1 by dividing everything by -1, right? Because if that happens, the 0 still stays the same. And then this is much easier to solve, which makes it it makes it so that you won't make the mistake as often. Because everyone makes mistakes. Even like the biggest pros make mistakes at some point. It's going to happen. I'm sorry to bring it to you. I make mistakes. Isha makes mistakes. Everyone makes mistakes. What makes people different is whether or not they catch their mistakes. So that's like a huge thing to do here. So yeah, that's all. But yeah. Okay. But now we have our next problem, which is out here. I thought it was really cool, actually. So it says here, suppose that a, b, and c are positive real numbers, such that ab equals a plus b plus b plus 20, bc equals b plus c plus 17, and ac equals a plus c plus 41. And I wrote down all the equations over here as well. What is a plus b plus c? Okay, so we see all of these a plus b plus c's over here, and we think, okay, what if we add them up? And we get 2a plus 2b plus 2c. I think that's actually a bad idea. You want to know why? Because I think we can actually solve for each of them separately. I'll show you. So what we do here is we're going to move all the variables on this equation to one side. We're going to move them to the left side. Then you get ab minus a minus b equals 20. Now at this point, what we want to do here for this equation is we would like to make this b nicer. So what we're going to do here is we want to factor it into a minus 1 times b minus 1. Because if you actually expand this, you get ab minus a minus b. But here's the problem. It doesn't actually work because we also get an extra 1 term. But that's fine, actually. You want to know why? Because we can add 1 to both sides. And that gives us, this is equal to 21. Okay, we can do the same with the other terms, actually. We can get the, this one over here is bc minus b minus c equals 17. Add 1 to both sides. You get b minus 1 times c minus 1 is equal to, 18. And then the last one is a minus 1 times c minus 1 is equal to 42. At this point, I think it's possible to literally just like try out a bunch of possibilities and see if it works. But I actually have a cooler way of doing it. What we're going to do is we're going to multiply all of these equations then. We're going to multiply them all. You'll see what happens. If we multiply all these equations, we get a minus 1 squared times b minus 1 squared times c minus 1 squared is equal to 21 times 18 times 42. Now, we're going to take the square root of both sides because we have all these squared terms. So that would give us a minus 1 times b minus 1 times c minus 1. Whoa, keep mistaking my parentheses to be c's. So that's bad. And that would give us this thing over here is equal to the square root of 21 times 18 times 42. That's annoying. Okay, well, let's try factoring this out. So we get 21 is 7 times 3. 18 is 3 squared times 2. And 42 is 2 times 3 times 7. And at this point, we see that there's 2 7s. There's 4 3s, actually. 1, 2, 3, 4. And there's 2 2s. So this whole thing is equal to 7 times 3 squared times 2, which comes out to be... Actually, you know what? No, we're going to keep it the same. You'll see why. Very short. So what we get here is that this is equal to 7 times 3 squared times 2. But we also know these things. So what we can actually do here is we can substitute a minus 1 times b minus 1 equals 21 into this equation. And so what happens then is that we get 21 times c minus 1 equals 7 times 3 squared times 2. So c minus 1 equals 6. So c equals 7. We can also plug in a minus 1 times c minus 1, which was, I believe that was 18. And that would give us 18 times b minus 1 is equal to 7 times 3 squared times 2. Therefore, c minus 1, or b minus 1, oh, I'm writing all over myself, that's bad. This is equal to 7, and so b is equal to 8. And finally, we can plug in the last one, which is a minus 1 times c minus 1. Oh, I must have gotten the wrong thing here. This should actually be a, because we're plugging in the wrong, okay. It's fine, because there's symmetry anyway, so it's not a big deal. But anyways, for the last one, you just plug in a minus 1 times c minus 1 equals 42. So that gives us that 42 times b minus 1 is equal to 7 times 3 squared times 2. And at that point, you would just get that b minus 1 equals 3. So then b equals 4. And now we solved for all of these. You got 7, 8, and 4. And their sum is obviously 19. So that's our answer. Perfect.
Awesome. Cool. Well, I saw this like interesting physics question in chat. And I feel like there's like a really easy like intuition way to think about it. And it's and I just wanted to like go over it real quick. So first, you basically need to find like the optimal angle. And you obviously know it needs to be between 0 and 90, because if it was like 120 or something, it's shooting off in this direction. And I'm pretty sure that we're just talking about like the angle if we're going in like one specific direction. Like we don't want to go backward, we want to go forward. So obviously it needs to be between 0 and 90. But you can kind of just like think about it like intuitively. If we pick something like 70, for example, then it's going to shoot up like this, and it's kind of going to, well, it won't come down in a triangle. It's going to come down in a parabola. It's kind of going to come down kind of like this. But if we do something like 10, it's kind of just going to do this like really like low arch. So the best way to optimize it would be to do 45 degrees, because you're going to get like a good like, I guess like balance between like the force that's going in the direction, but also like not making sure like gravity pulls it down too fast, because you want to give it enough angles that it goes off, but you also don't want it to come down quickly. So I feel like the optimal would just be 45 if you just think about it intuitively.
Okay.
Yeah.
I saw a question here, and I'm not sure. It might be a troll again. Like, guys, trolling is not funny. Okay, it's kind of big, but it looks cool. So I want to try it, at least. I want to try it, but maybe I'll fail. We'll see. Failure is okay. But okay, so we have triangle ABC. With BC equals 20 and M is midpoint in BC, right? So we have M, these are 10 and 10 because it's midpoint. And then L1 passes through B and C and are both perpendicular to line M. Okay, so they're both perpendicular to this nice line. Okay, and then what we want to do is we would like to find the smallest positive real K, such that for any triangle with ABC and area K, at least one of the following is true. L1 meets AC, or line L2 meets AB. Okay, it seems to be true, actually. It kind of seems to be like that would be the case. But you know, we're mathematicians here. We don't want to like take anything for granted. So let's see how this works. What if we take a more extreme case? Well, what if we took like an obtuse triangle, for instance, right? So this one would be there. And then this height is there. and there. So it does seem like the obtuse triangles also work. And that kind of makes sense because, okay, so here's a few interesting facts about altitudes in general. So essentially, if you have a triangle, if you have a certain triangle here, right? And then you want to like drop the perpendicular here. What really matters is the side length, the angle of these other two ones. And that will impact whether or not this perpendicular passes through the segment, if that makes sense. Because like okay, so I'll give some examples. If we had like an obtuse triangle, then obviously the altitude passes outside of this. So yeah, but with this one, for instance, because these two are both acute, it will actually go right through. And if you have the equality case where it's essentially a right triangle, then literally the altitude is the leg of the triangle. So that's obviously inside of it. So yeah, so essentially, in order for it to not pass through like, in order for both of them to not pass through, there has to be two obtuse triangles, right? There has to be two obtuse angles in there. Okay. And more specifically, actually, these two triangles, so like this triangle, AAMC and ABM, need to both be obtuse. And moreover, actually, the obtuse angle cannot be B or C. So we also know that that B and C, angles B and C, must be acute. Okay. Interesting. Well, what this means, oh. Okay, so what this really means now is because so if we were to like fix segment BC, which we can do because we actually know how long BC is and we know exactly where M is. What this means here is that we have these like perpendicular lines, and A has to be within these lines. A has to be here. Because if A was like over here, for instance, or if it was over here or whatever that is, then that wouldn't work anymore. Because that then B, one of B or C would be obtuse. And at that point, we already know that it has to pass through, right? The way you know that is by drawing out the obtuse triangle and just seeing, oh, look, the altitude passes through. And that makes sense to us. Because, yeah, so if A was here, basically, if A was here, then we already know ABM is obtuse. And then that already solves the problem. Okay. Okay. What if angle A was obtuse? What if it was like this, for instance? Would that still work? My conjecture is yes. And that's because if you were to draw this, then we can actually see here that one of these, in fact, must pass through it. Right? Like one of these has to, because these are all like one of these two must be acute, and this one of these two also must be acute. Wait. Hold on. That's false. I just realized. Okay, I think I understand this problem now. I think I fully understand now. The idea here is, oh my gosh, it's so cool actually. So the idea here is that this one, yes, the real limiter is ABM. And that's because angle A here, BAM, that must be obtuse. It must be obtuse. There is no other way. It has to. And so what this means, therefore, is that this only works whenever ABM is obtuse. And so essentially what we can do here is here, I'm drawing so many diagrams. So essentially, oh my gosh, I actually love this problem now. So what this means here is BAM must be obtuse. And the way we can find all the points that have that satisfy this property is by drawing a semicircle. And the reason for that is by a well-known theorem. Essentially, the theorem states that if a point is on this semicircle, then BAM is in fact right. And it's actually pretty easy to prove. The way you do that is by drawing out the full circle. And then note here that this arc is 180. And this is actually an inscribed angle. And so what that means is that the inscribed angle is half of the arc. So the inscribed angle must be 90 because the arc is 180. Now, what that means, therefore, is that any point A that's inside of this circle, that's in this circle, must be obtuse. It must be, BAM must be obtuse. And so what that means then is that these don't pass through it. That the altitude does not pass through AC anymore. So no, does not work. Therefore, A must actually be outside of this circle. It must be somewhere over here. And so what that means basically is that anything, any height, the height of A must be above this. It must be above this line, which is basically the line that's tangent to this thing. Essentially, this A, the height of A, must be bigger than the radius of this circle, because that is the radius, and it must be above it. Therefore, all they gotta do is find the radius. And that's easy, because we know that BC is 20, BM is 10, and the radius is 5, because BC is the diameter. Therefore, the height must be 5, height, or at least 5. And since we know that the base is exactly 20, that means that the area must be at least 20 times 5 over 2, which is 50. 20 times 5 over 2, which is 50. That is the minimum answer. So yeah, that's what it is. All right.
That was a super cool problem. All right. So I thought this one in chat, I thought it was really interesting, especially like after like I thought about it for like 1 or 2 seconds. And when you ask like, does there exist? All you really need to do is prove one test case that it is true. So if we're able to find something that proves this thing, then we're done, because we know that the answer is true. There is something that exists. So I'm gonna begin with knowing that like if you take like square root of 2, or you can take like square root of 3, for example, times square root of 3, that's gonna be equal to 3. Obviously, that can't directly work here because we're using a to the power of b, but I feel like this is going to be useful because it takes like these two like irrational numbers and turns it into a rational number. So we can continue this property by saying, well, let's set a equal to, I'm going to go back to square root of 2 because it's like a really nice, easy, it's just a nicer number in my head. All right, so if I set a equals square root of 2 and b equals square root of 2, then square root of 2 to square root of 2. If you knew what this is, I'd be very surprised because I don't know what it is. And well, okay, that obviously doesn't mean that you don't know what it is, but like it's a weird thing to know. So I guess what we could do is we could assume that it is irrational. And then if we assume that this is irrational, because if we assume it's irrational, then we're done and we basically didn't do anything with the problem. But if we assume it's irrational, then what we could do is that we could assume that this is one of the two irrational numbers. Because the thing about this is that if it doesn't exist, that means it must work for every single two irrational numbers. So what we can do is we can say, well, a sub 2 is equal to square root 2 to the power of square root 2, and b is equal to the square root of 2. And that solves our question because it goes back to like the principle that I just explained right here. Because what we can do is we can say, well, a to the 2 to the power of b is equal to square root of 2 to the power of square root of 2 to the power of square root of 2. And then for those of you who like don't know this property, there's like an exponential property where it's like if you have a to the b to the power of c, that's just a, b, c. So you just multiply them together. So then here you're going to get square root of 2 to the power of square root of 2 times square root of 2, which is 2. And then, oh wait, no, sorry, square root of 2 to the power of 2. And you're like, well, we don't know what square root of power of 2, square root of 2 to the power of 2 is. But do we really need to know that? Let's go back to what we initially set our condition as. Square root of 2 to the square root of 2, that was our test case. So this is test case 1. And this is test case 2. Can we find test case 1 within test case 2? Well, it's right here. Let me use a different color. Right here. That's test case 1. And we just found out that it was 2 because we just like solved that within test case 2. So that means this must be rational. And therefore, the answer to this question has to be true because we just proved one test case and that's all we need. So yeah.
That is so cool. Like when I first saw it, I thought, wait, no, there's no way this is middle school level. And I realized, oh, like as you were solving it, I realized, oh my gosh, that is so smart. Okay, it's so cool. That's a great solution. Okay, I saw this earlier as well. And I thought as well, actually, that it might have been too hard, but I think it's not terrible now. Okay, let's see. So the biggest thing to realize with this question here is that P has to be 3. And actually, before you do that, let's read the question. So 9xy equals P times P plus 3x plus 6y. Find the maximum positive value of P squared plus x squared plus y squared. Okay, so essentially, my reasoning behind the fact that P equals 3 is look at this. Left side is 9. Right side must also be divisible by 9. If it was not 3, then, well then, P times P plus 3x plus 6y. So then if P was not 3, then this would not be divisible by 3, but neither would this, because these are also multiples of 3. So P has to be multiple of 3. Exactly. And because P is a prime, because P is also a prime, that means P has to be exactly 3, because if P was greater than 3, it wouldn't be a prime anymore. So that means that P equals 3. Perfect. And we can now simplify this even further to give us 9xy equals 3 times 3 plus 3x plus 6y. And now we divide everything by 9, which would give us xy is equal to 1 plus x plus 2y. Okay. Now this one over here, we have to find the maximum possible value of 9 plus x squared plus y squared, which is basically the same actually as just finding x squared plus y squared and then just adding 9 to it, because we can do that pretty easily. Okay, great. Let's see, how does this work now? How can we find that? It's kind of weird. Let's see. Well, we know that x and y are actually positive integers. Yeah, that was, I think I forgot to put that in, but yeah, they're positive integers. And so we get from here that this is actually a nice integer equation. So if we were to factor this out, first let's actually move everything to one side. And now if we were to factor this out, we can do it with what's called Simon's favorite factoring trick. And how it works is you want to put this into this form because x times y is xy, x times -2 is, wait, hold on, no, I did this wrong. I'm sorry, I messed up. Restart. Okay, we want to put this into the form x minus 2 times y minus 1. And the reason that works is because x times y is xy, x times -1 is -x, -2 times y is -2y. And now the problem with this though is that there's also a -2 times -1, which is just 2. So we have to add 2 to both sides to get this to be equal to that. And that means that the right side is 1 plus 2 or 3. Oh wow, that's a big message. What the heck? Okay. So yeah, now we get this. Perfect. What we can do now is we can actually find x and y. And the way we would do that is like this. So because x and y are integers, x minus 2 and y minus 1 must be factors of 3. And there's actually not that many factors of 3. There's 1, 3, 3 and 1, -1 and -3, and -3 and -1. Okay. Okay. So now, if this whole expression is 1, what that means is that x must be 3, because 3 minus 2 is 1. If this expression is 3, that means that y must be 4. And that's kind of, yeah, okay. X is 3, y is 4. That works. Next one. For this one, x is 5, because 5 minus 2 is 3. And for this one, y is 2, because 2 minus 1 is 1. Okay. And then for this one over here, for this one, actually, we also know that they're positive integers. And so we can already tell here that from -3, y must be -2. So this one doesn't work. And same for this one, actually, because x would have to be -1. So it wouldn't work because they have to be positive integers. So these don't work either. And so we're left with two options. X and y are 3 and 4, or x and y are 5 and 2. For the first one, x squared would be 9, y squared would be 16. So this would be 25 total. And for this one, x squared is 25, y squared is 4, so it's overall 29. Clearly 29 is larger. Therefore, the answer must be 29 plus 9, or 38. Perfect. All right.
Cool. That was super like interesting. And I like how you use Simon's factoring trick because that's like a really like cool, interesting factoring like method.
I agree. It's so awesome.
All right. So this one like was like one of the very first ones, and I apologize for like missing it earlier, but luckily our mods caught it and was I'm here to solve it. So how many ways can you put a bagel in a 4x6 grid so that every column or row has at most one bagel? And the very important part here is that it says or, because if it was like column and row has most one bagel, it would be like a lot more easier because you just like put it in like some alteration of diagonals or something like that, which we're gonna come back to because we need it to solve this problem. But what I was thinking with this is that we break it up into separate cases. Our first case will be every column. The next case will be every row, and we just add those together. But we need to subtract the ones that are column/row. And then, so in order to like tackle the column, this is particularly interesting because it's like a 4x6. They can't just do like 2 times like column or something like that. But so I'm just going to assume that in this diagram I have 6 as the column. So I'll just like stick with my diagram here. So in order to find out how many ways you can put, oh, it doesn't give you a set number of bagels. Wait, can't you just like put one bagel then? Do you have a set number of bagels? Oh,
Wait, I think there was set. Yeah, I think there was a number. But
yeah, because otherwise like you're just gonna get like a whole lot more cases.
Yeah.
Wait, does the person who sent the question mind clarifying whether there's a set number of bagels or not? Let me see whether I can find the original problem. Wait, yeah, I can solve. Okay, I'll just solve it like assuming that like you. Yeah. Okay. No, actually, any number of bagels works, but you can just choose 6 if you like. Yeah. Okay. Yeah, that kind of made sense because I don't think you need to know the set number of bagels for this question. All right, let's just continue, and then we'll see whether we need a set number of bagels later. I just love how much and many times I have to say bagels in this question. It's really fun. Anyways, column. So the number of ways you can put a column. Well, for every single column, there's 4 spots on where you could put it. Right? You can either put it in like the first row, second row, third row, or fourth row. And in this specific case, we don't really care how many bagels. Like we don't care whether or not it's in the same row. Like you would put like all the bagels here, like I don't care because that I'm going to consider that in my row case. So that means that for each one of the 6 columns, there's going to be 4 spots that you could put the bagel. And then also, if we want to consider not having that many number of bagels, you could also just put it to the power of 2, saying that like there is like there's okay, give me a sec. Basically 2 to the power of, it would just be 6 because you can choose whether or not the bagel is on or off, meaning whether you have it in that column or you don't. So I'm pretty sure that that would just be to the power of 6. No, that's wrong. Because that means that you're multiplying 6 to the power of 4 to the off cases as well. So that's definitely wrong there. But you could just like break it down into to the power of 0. Wait. No. Wait. That's weird.
Wait, what?
Because no, because what I'm trying to do is that I'm like, if we don't have a set number of bagels, you have 2 to the power of 6, because for each column you choose whether or not there's a bagel. But if there's not a bagel, then you're not multiplying 6 times 4 to it. So yeah, that's the weird part about this.
Wait, I'm confused as well, actually.
Because like, how would you account for the
I think we should go with set number of bagels. Like, just go with
Yeah.
6. Yeah,
Okay, yeah.
best.
In the chat, it says that is I think microscopic mouse, amazing name by the way, says 6 is good. So I'll just set it as 6. All right. Wait, that means you can't do rows, because that means you are going to have 2 overlapping. Okay, that makes the question easier, I guess. Because if, okay, sorry, I'm sorry if I was confusing everyone, but let's just restart now that we have a set number of bagels, because it's going to make it a lot easier. Okay, so if we have 6 bagels and we're trying to put it in every row, then that's going to be 1 per row, and then you're going to have 2 left over. And that means that you're going to have to put it in one of those rows. So that means you can't have the row as the case here, because you're going to have 2 that's going to have to be in one of the rows, because you're going to have 4, and then you have to put the other 2 with something. So that means you have to consider only the columns, which goes back to what I was saying earlier. For every column, there's 4 spots which you can put it, because it's or we don't have to care about the rows. So I think that's just our answer, because we don't have to consider rows, which means we don't have to consider both columns or rows.
That is so cool, actually.
I feel like that's
Okay.
oddly simple, but I'll go with it.
Yeah, it's probably true, actually. Okay, I got a weird question here. Why are you guys giving me all the geometry questions, you know? It's kind of mean.
I mean,
I
to
have
be
a
fair,
comma.
I'm selectively not picking geometry because I know I'm gonna suck at it, but
Come
you
on.
can blame the students. That works for me.
Okay. It's everyone's fault. Yeah. Okay. Triangle ABC has measure C equals 90. Point H is the foot of the perpendicular from C to line AB, and point D is on line AB, such that line CD bisects HCA. Given that HD equals 1 and BC equals 5, what is AD plus AC? Okay. Well, what we can do here is, I think we can let AD equals X, maybe. Or no, even better, actually. Let's let HC equals X. And you'll see why in a moment. Because you see, here's the power of this. We have a lot of right angles here. And whenever you see right angles, you know what you should think of? At least with like a triangle. You should be thinking of similar triangles, because there are actually a lot of similar triangles here. Specifically, what's happening here is because angle C is 90, but also angle H here is also 90. What that means then is that triangle ABC is similar to triangle, what is this? CBH. And the reason for that is because we have here that angle H and angle C are equal. And obviously angle B is equal to angle B. So what that means then is that these two are similar. And we can actually add a third triangle. You want to know which one it is? It's A, C, and H. And that's because we can just sort of add in that other right angle here. And that's perfect for us, because you can see here, we have a lot of similar triangles. And that's good, because in geometry, we love similar triangles, right, guys? Okay. So specifically, it would be ACH in that order, I think. So yeah, okay, perfect. What that means now is that BC over CH would be equal to, here, let me move down. BC over CH is equal to AC over AH. Wait a minute. Hold on. BC is 5 and CH is X. AC is this thing over here. Huh. Let's let it be A. Actually, Y. Y is better. So then Y over, oh my gosh, there's too many things here. I don't like this. I don't like this a lot. Let me think here. Okay. Okay, what if we solved for AH? So we're gonna keep this as AH anyways. And then what that means now is that this becomes AH is equal to XY over 5. So this whole AH over here is just XY over 5. Perfect. Okay. That is XY over 5. But moreover, we also know that this thing over here is the square root of 25 minus x squared from Pythagorean's theorem. Pythagorean's theorem. Yeah. Okay. And so what this means now is that AD is xy over 5 minus 1, and BD is square root 25 minus x squared plus 1. Oh my gosh, this is not pretty. This is not looking good. I don't like this. That's fine though. That's fine. So now, because of angle bisector theorem, which means that this is equal to this, oh, sorry, this divided by this is equal to this divided by this. When I'm saying like, sorry, already done actually, it's probably the same. So AC over AD equals BC over BD is what it says here because it's a big angle bisector. So what that means now is that y over xy over 5 minus 1. Oh my gosh, no, this is bad. Is there another way of doing this? I don't want to do that. That looks very scary. Okay. Maybe we can have a different approach here. Okay, let's restart. Let's restart. I think what we did wrong here, what I did wrong here is that I set the wrong stuff. Well, it's not right triangle. Hold on. I set variables to the wrong things. I think now that we have more experience with this problem, maybe we can set the right variables. Let's find out. Okay, let's do the same thing. Wait, is that right? No, it's not right at all. Should be like there, probably. So that would be H, that would be D, and we get here, that's 1, this one over here. Okay, we're gonna set different variables now. Is that true? Hold on. It was BC equals 5. BC equals 5. Okay, BC equals 5. And so what this means now is we want to set the right variables now, okay? Because we don't want to have wrong variables like last time. So we're gonna give this one be X. And we're going to let this one over here be y. And the reason for that is because now we have x over y is equal to 5 over this thingy over here. And so what that means is that BH is going to be y, 5y over x. Because y over x is equal to BH over 5. And so that gives us 5y over x as this. Right. Okay, and that gives us here, or well, actually, hold on. It wouldn't be this actually. It would be just that. Okay, okay. So now what we also have though is that AH to AC should be equal to CH over CV. Ah, see what's happening here? We just have the wrong similar triangles because we're getting this nasty CH expression, which is like a lot of variables. I don't like it. I don't think there's a way out of this. I don't think it's really possible to get out of this nicely. Wait. I got an idea. No, it doesn't work. Never mind. That doesn't work. Okay. Okay. So instead, what we're gonna do here is we're just gonna go for it. Why not? Let's do it. So CH is square root of x squared minus y squared. Not too bad. Hopefully that it gets better. And then CH is also, though, 25 minus 1 plus 5 over y, 5y over x squared. Oh my gosh. Oh no. I have no clue there's no way out of this. Oh my gosh. Okay, but that's not terrible. Yeah, actually, that's not even that terrible, because what you can do now is you can use similar triangles to get another relationship between ACH and BCH, and then with enough calculation and brute force, I think it's definitely possible to solve this problem. But considering how much time that would take, I think it's best if we just move on now. So yeah, it is not a nice equation, but I don't see another way out of this.
Yeah, like yeah, that once you got to the end of your solution, I think that's just going to take brute force, which we don't have the time for.
That's true.
But I do think we can solve this question in the last 5 or so minutes that we have. So basically, you have a friend with I don't want to attempt to pronounce their name because I don't want to mispronounce it. Has 6 cards and loses 1, and you just want to find how many ways you could make a 5-digit number. So essentially what you're doing is that you're choosing 6 of these numbers, and you're seeing how many ways it's going to be divisible by 6. The most important part to consider here is that 6 is 3 and 2. So all you really need to do in the 5-digit number is to make sure that last digit is divisible. Okay, if I'm pretty sure you all know this, but the divisibility rule for 2 is just that it's an even number. For 3, you need to sum up the digits, and if that's divisible by 3, then the whole number is divisible by 3. So the 2 one is very, very straightforward. If you have like a 5-digit number, we have 2, 4, and 6, and either one of those 3 can be the remaining digit. And oh, sorry, this is supposed to represent possibilities, not like the number it is. So 2, 4, or 6. And then I think for each one of these numbers, we need to consider what the sum of the other numbers are, because yeah, that's the only thing that really makes sense to me, because like these this is 1 apart, this is 2 away, and this is 3 away. All right, so for this one, we have 1, 2, 3, 4, 5, 6. We've already used 2, and we need to sum it so that it is 1 less than a divisibility of 3. So that means, or actually, yeah, sorry, 1 more, because we need to account for the 2. So that means that I think that if we just do like a little bit of like test cases, we'll be able to find out like the pattern and then do it accordingly. So it's going, an example that would meet this would be 3, 6, and then, wait, no, that wouldn't work because 4 and 1 doesn't work. Okay, wait, I think that wouldn't just, okay, I have a simpler thought. If this kind of aligns with what Dingle said in the chat, if we're just able to find out all the total ways you can pick 5 numbers from like 4 of the 5 numbers, so it's going to be 5, choose 4, then 1/3 of these are going to fit 2, 1/3 of these are going to fit 4, and 1/3 of these are going to fit 6, because this is 1 apart, this is 1 below, this is 1 above, and this is exactly. So that means that it's just going to be 5 to the power, it's going to be 5 times, it's just going to be 5, right? No.
Wait, I think, okay, a simpler way of thinking about this is that in order for a number to be divisible by 6, it has to be divisible by 3 and 2, right? So for 3,
Which is what
it has, yeah, exactly. So then for 3, the sum of the digits has to be divisible by 3. So you have to either discard 3 or 6. And for 2, the last digit needs to be either 2, 4, or 6. So all you gotta do now is just do casework. Either you discard 3, so either you discard 3, or you discard 6. And if you discard 3, then there's 3 ways for the last digit and 24 ways for the other digits because you have 4 digits left and it's 4 factorial. And then for the 6, there's just 2 ways for the last digit because it's even, right? Because you only have 2 or 4. And then times 24 for the other ones. So overall, it would be 5 times 24 or 120. So, yeah.
Oh yeah,
right?
sorry. That's definitely much easier than what I was trying to do.
Yeah, it's okay. It's okay.
All right. So it is 4 o'clock. So we really enjoyed being here. And the next Ask About Anything is going to be right after this live show ends. You're going to see like a screen with the next 4 events. So make sure to come to the next Ask Math Anything.
Yeah, awesome.
Yeah.
All right. And I think Professor Lowe will come back now. So, yeah. Goodbye, everyone.
Goodbye.